ऊपर रखना, ऊपर ही ठीक रहेगा, क्योंकि नीचे उतार दिया तो भारी पड़ेगा।
So good evening, everyone.
युवा
I would like all of you to actually switch off your video cameras as of now. So I see that 4 of you have joined. So let's wait one more minute and let's see if other people are joining or not. So am I audible right now?
रात को हमारा ये फायर होगा, बाद में मुझे तो यार ये बिगड़ेगा तो कुछ कम दिखता ना हो जाता, हम यार मैं तो उसके समझ रहा
Anyone
हूँ
on
थोड़े
stage?
पीछे बढ़ेंगे तो वहाँ लड़ा गया। हाँ तो हम यहाँ पीछे
Am
बढ़
I
गए
audible as of now?
ना।
Okay, thank you. So is this presentation is visible to you guys? Right, it is presenting. Okay. So good evening, everyone. You are all welcome here in the first live session of Biointerface Engineering. And this course is being taught by Dr. Lalit Mohan Pandey. He is the Associate Professor in the Department of Bioscience and Bioengineering, IIT Guwahati. I myself am Shilpa Nandi. I am working as a research scholar in the Center for Environment, IIT Guwahati itself. I hope that I am audible, as well as let me just switch on my camera for once now. Okay, right. So if you are not able to see the presentation at any point of the session, or you're not able to hear me, just raise your hand and or just mention in the chat box about the same, so that one-to-one interaction is like goes on smoothly. So this live session is all about the week 1 assignment. So for this course, this was firstly run in January 2021. Then next it ran for January 2022, and this is the third time it has been run in the NEPTEL platform. However, I think that week 1, week 2, as well as week 3 assignment has been uploaded right in the NEPTEL in the Swayam MOOCs course. So let me give a brief brief understanding of what are we going to just do in this session. So this is basically a doubts and interaction session, which will be conducted every week. That is every Tuesday from 7 to 9 p.m. You all are encouraged, if you have any doubts regarding the course or even the questions that has been uploaded, you can just uh, even write it here, raise your hand, unmute yourself and raise a query, or that the questions can be posted in the chat box. So you all know what the discussion forum for the course is. So any question related to the live session conducted can be raised here. These questions will be either addressed in the forum or in the next week's live session. So you guys know from where you can just go to the discussion forum, right? If not, let me just show you. So this is the course, and see, you can see here this tab that is ask a question. You can just click on this and post any of your queries in this one. Apart from that, I think you know well how to use Google Meet. So raising your hand, unmuting yourself, and raising a query is not a big deal here. But I'll show you once. So this is the hand, as you can see. You can just raise your hand and ask some questions. Okay, so I see 3 people has joined. So let us just start the session. So the outline of this live session is will not actually go through completely the content recap. However, I will point out what were the main things which were discussed for week one specifically, which contained of 3 lectures. That was intermolecular forces. Next was classification of intermolecular forces, and third one was thermodynamics aspect of intermolecular forces. Now, next we'll mostly be talking about the week one related assignment questions and answer discussion. So, we won't specifically discuss the assignment questions which are being uploaded at this current semester. However, I will try to discuss very similar questions to those, such that that will help you to solve the questions that has been uploaded right now. So, any problem, any issue till now? Uh, Priya, Sonali, Samuel.
No, ma'am.
Okay, thank you. So next, let's move on to the first question. Okay, so before going to the question, let me go through the quick revision of week one contents. So firstly, in the lecture one, intermolecular forces, you all studied about the 4 forces of nature. Next was the model interaction potential, total interaction potential, as well as the equation of state and pair potential. Next, I think we classified the intermolecular forces, that is the covalent forces as well as the charge-charge interaction, dipole-dipole interaction, self-energy, ion dipole interaction, and charge dipole interaction. And lastly, in lecture 3, you all studied about the self-energy as well as the Boltzmann distribution in terms of chemical as well as number density and solubility. Right. So let's move on to the first question. So the question here is, van der Waals forces are also termed as, option A is dispersion forces, B Keeson interaction, C Debye forces, and lastly all of the above. So anyone from you guys would like to answer
Option
this?
C, ma'am.
Option C. Okay.
Yeah.
Well, you are right. Option C is also termed as van der Waals forces. But dispersion forces as well as Keesom interaction are also termed as van der Waals forces. So it's not just Debye forces, which we know as van der Waals forces, but the correct answer would be all of the above.
Okay, ma'am.
Right. So we'll see. So as you can see, dispersion forces are basically the London dispersion forces. These arise due to the interactions between an instantaneous dipole and an atom or molecule. So these forces were named after the German physicist, that is Fritz London, and are also known as instantaneous dipole-induced dipole forces. So these forces are believed to be the weakest of all the van der Waals forces, and the strength of these forces are between the two atoms or molecules depend entirely on the polarizability of the atom or molecule. So in case of Keesom interactions, these can also arise due to electrostatic interaction between the charges in ionic molecules, interaction between dipoles in polar molecules, as well as the interaction between the permanent multipoles. So these forces were named after the Dutch physicist Willem Hendrik Keesom. And lastly, it's the Debye forces. So Debye forces are caused again by the interaction between the permanent dipoles and other atoms or molecules, which result in the formation of induced dipoles. For example, an induced dipole can be formed from the repulsive forces between the electrons and a permanent dipole. So these were again named after a Dutch American physicist, that is Peter Debye. So the answer to the first question is all of the above. Sorry. So we'll move on to the next one. So next question is, which of the following is true for van der Waals forces? So the options here are covalent bonds and ionic bonds are significantly weaker than van der Waals force. Van der Waals force are short range forces. Option C is these forces may be repulsive or attractive, and option D is they are additive in nature. So anyone would like to again answer this question? So think about the characteristic of these forces. What are the characteristics of these forces? And then think about what can be the answer. Any guesses, like any minute guesses? So the question here is like which is true for van der Waals forces? So any one of among this one is true. I know this session is going to be a longer one. I would like to like complete this one. I don't have like much questions. Like I will discuss 10 of the questions, and then we can just discuss any other like queries if you have regarding these particular questions as well as whatever you have learned till now. Okay, so the correct answer for this is option number C, that is these forces may be repulsive or attractive. Right. So why this option C is correct and why not other options are correct, we'll discuss it. So option A tells here that covalent bonds and ionic bonds are significantly weaker than van der Waals forces, which is not true. So here it is that the covalent and ionic bonds are significantly stronger than the van der Waals forces. Why so? So the strength of a covalent bond, I think you must have learned in the classes as well. It might have been taught that what is the strength of these covalent bonds. So it ranges around 200 to 800 kilojoule per mole, whereas the strength of the ionic bond particularly ranges from 170 to it can even range till 1500 kilojoule per mole. Whereas for the van der Waals forces, the strength lies only in the range of zero point 0.4 to 4 kilojoule per mole. Hence, we rule out our option A. Next, when we see the sentence here is van der Waals forces are short range forces, which is not true. Why so? Because van der Waals forces are long range forces. They are long range forces, and depending on the situation, it can be effective from large distances, that is greater than 10 nanometer down to interatomic spacing about 0. 0.2 nanometer. So the third option, which was the correct option here, said that these forces may be repulsive or attractive. So in general, the dispersion forces between any two molecules or large particles does not follow a simple power law. Hence, it can be either repulsive or either attractive in nature. And lastly, they are additive in nature, which is also again not true, as these forces are non-additive in nature. That is, the force between the two bodies is affected by the presence of other bodies nearby. So this is called the non-additivity of an interaction. So any queries till now? I think the questions are quite easier for the week one. I've tried to incorporate a theory bit in these session. We'll also discuss some numerical questions. So I hope everything is clear till now. Okay, fine. So now let's move on to our next question. So, uh, wait, just let me ask you one thing. Okay, you can see the slides being getting changed, right? Or is it stuck at one point? I hope the slides are changing when I'm speaking and it's not stuck. Probably. Any questions? Repulsive. Okay, you gave the answer for repulsive and attractive. Fine. Actually, I didn't get the message. So, okay, I'll look into the chat box as well. Okay, fine. So, let's move on to the third question. Third question is, my potential is also termed as NM potential, interaction pair potential. Third is Lennard-Jones potential. And fourth is both A and B. So you guys can recall yourself like what was my potential? Can you just recall it? What was the equation related to it? So then you will try to answer this question better.
Ma'am, option B, interaction pair potential.
Okay, fine. Thank you. 726. Okay. So from Samuel also I am getting the same answer, that is option B, which is interaction pair potential. Fine. So I think that you guys have got you guys have the book relating to this course or not?
No, ma'am.
No. Okay. So I think Neptel from the Neptel side you will be getting one drive folder where I will be uploading all these presentations. So in that I'll try to upload the book as well so that you can just get the access of it. So once you will have the book, it will be easier for you guys rather than just going through the videos which are being uploaded in Neptel. However, in the Neptel site, I think they have mentioned about book, right?
No,
About uh,
no. Actually, every week is only lecture is there. 3 lectures.
okay.
in
Yes,
videos.
lectures are there, but in the site, in the like course, in the Swayam portal, I think, see, uh, I think it's there. I think if you search in the site, you will get it. But most probably, I'll be just uploading the book for this, PDF for this as well.
Okay.
I'll try to upload it as soon as possible because already 3 weeks have gone and like the third week contents has been uploaded. So,
Yes,
okay,
ma'am.
let's move on. So the answer here is yes, interaction pair potential is the correct one, but NM potential is also the correct one. So the true answer for this question is last one, that is both A and B. So we'll see why the last one is correct. So I think this they might have taught you this in your course. So what is my potential? My potential, it was given in 1903 by Wayne Mai. Okay, so this basically gives the equation for interaction pair potential, and it is also known as N and M potential because as you can see, the equation is WR is equal to minus A by R power N plus B by R power M. So this N and M, here we can also uh, refer this my potential as NM potential. And why not Lennard-Jones potential? Because this is a special case of my potential where interaction potential is equal to minus A by R to the power 6 plus B by R to the power 12. So this was proposed by Lennard-Jones in 1924, and my potential was actually proposed in 1903. So Lennard-Jones, after the quantum theory, had shown that the attractive exponent in the my potential is 6 and the inverse 12 exponent was chosen for mathematical convenience. So it been shown that any number within 14 plus minus 5 gave equally good agreement with the experimental data available at the time. So the answer, so the correct answer for the third question was both A and B. Fine. Okay. I think this is quite clear why my potential is also called as interaction pair potential and NM potential. Okay. So let's move on to the next question. So next question we have is, just wait a minute. Yes. So the next question is, the structure of DNA is stabilized by which of the following forces? So the
Ma'am,
options.
hydrogen bond and covalent linkage.
Okay.
But there is a option is only hydrogen bond.
Okay. Okay, fine. Right. So yes, you're right. Sorry, I forgot your name. Let me look into it. Yes, Sonali, right. So you are quite right. Hydrogen bonds, and as well as there are several other forces which are acting in the DNA. So we'll look into it. So let's just discuss this. So the options are van der Waals forces, second is hydrogen bonds, third is hydrophobic interactions, and lastly it's the all of the above. So the correct answer for this is all of the above. So we'll see why all of the above is the correct one. So in case of the structure of DNA, van der Waals forces also plays a quite significant role. That is, in between the base pairings on the neighboring rings of the double helix, it holds the bases at an optimal angle to pack the double helix compactly. So as you said, the second option, hydrogen bonds. So you might be also knowing the reason behind it. Why so? Because they are present between the complementary organic bases. Basically, they form the base pair between, for example, between the adenine and thymine, there is like two hydrogen bonds are available, and between guanine and cytosine, uh, it is three hydrogen bonds are available. So next is hydrophobic interaction. So these are present between the nitrogenous bases as well as the surrounding sheath of water. So I guess it's now clear that all of the above options were true, and all the three forces are helping in the stabilization of the structure of DNA. Fine. Okay. So now let's move on to the next question. The next question is, which of the following does the Boltzmann distribution equation helps to find? So our options are A, chemical potential, B is number density, C is solubility, and D is all of the above. So which among the following does the Boltzmann distribution equation helps to find? Try to recall what was the Boltzmann distribution equation was. So I guess in lecture 3 you might have studied about Boltzmann distribution equation.
Number density.
Okay.
And there's a chemical potential. Uh, I have to find the option B.
Okay. Fine. Um, and Samuel, do you have any suggestion or any guesses for this question? Okay, fine. So the correct answer for this question is option D, which is all of the above. So using the Boltzmann distribution equation, we can find the chemical potential as well as the number density and also the solubility. So let's see how can we find this. So you might have seen that the Boltzmann distribution equation is mu plus kt log x1 is equal to mu2 plus kt log x2. So in case of chemical potential, mu is the chemical potential here. So it helps to find you the chemical potential. So you can replace the x1 and x2 with number density, that is rho z and rho naught. So the equation will then convert as mu plus kt log rho z plus is equal to mu naught plus kt log rho naught. And also the solubility here is the x1 and x1 is for phase 1 and x2 is for phase 2. Wait a second, I think someone is here to. So I hope this is quite clear that using the same equation we can find all the three, that is chemical potential, number density as well as the solubility. So this was all about the Boltzmann distribution equation. So we'll move on to the next question. I think few people are joining quite late, but it's fine. However, because the whole session will be also uploaded in YouTube, you can even go from there and view it anytime. Apart from that, I think the Neptal team will give the link for accessing the videos as well as the PPTs. Okay, so now the next question. The value of 1 dBi in coulomb meter is, you can see the options like A is 3.336 into 10 to the power minus 30 coulomb meter. Next is 1.6 into 10 power minus 29 coulomb meter. Another is 1.6 into 10 power minus 19 coulomb meter. And lastly 3.335 multiplied by 10 power minus 19 coulomb meter. So what is this d by? D by is the unit of D by is the unit of, any guesses? I think this has been like, this is basic chemistry. You might have learned it in class 11th or 12th, I guess. So if you try to recall, dipole moment has its unit as d by. Yes, Samuel, you are correct. Dipole. So dipole moment has the unit of d by. So now try to recall what is actually dipole moment. So then if you once recall what is this dipole moment, you will try to give the answer to this question. Okay, fine. So okay, the correct answer for this question is option A, that is 3.336 multiplied by 10 power minus 30 coulomb meter. We'll look into it how this value came for 1 dB in coulomb meter. So as you know that dipole moment is can be related as mu is equal to q into L, where q is the charges present and L is the length between those two charges. Mu is equal to q into L. Now anyone can you just give me what can be the value of this q? I think it's quite visible in the slide, but and what is this q? So q is basically the charge on an electron, right? So the charge on an electron is it basically values at around 1.602 multiplied by 10 power minus 19 coulomb. And taking the distance between these two charges as 0.02 nanometer. Can you just try to calculate this and give me the answer? Just try to remember that the question was in coulomb meter and not coulomb nanometer. Fine. We'll try to solve this one. I hope my screen is visible to you all. Right.
Yes, ma'am.
It's visible. Okay, fine. So the pen is not working. Just wait a minute. So the pen here is not working as of now. I'll try to take a 5-minute break in between. So we can solve this question without using this pen, but later on we'll be requiring it. So 1 dy is equal to mu is equal to q into L, where q values at 1.602 into 10 power minus 19, and the distance between these two is 0.02 nanometer. So first try to convert this 0.02 nanometer into meter and then solve the question. So it will be probably 2 into 10 power minus 11 meter, right? So multiply 1.602 into 2 and then 10 power minus 19 into 10 power minus 11. So the value will come at around 3.336 into 10 power minus 30 coulomb meter. I think this is not that tough of a question because we need to just multiply the two values. I hope without the pen also we can work for now. Is it clear, or shall I try to calculate it? Like in a blank sheet. So any answer, then I'll move forward. If you're not able to understand this question yet, please let me know. Okay, fine. I think all of you guys have understood this one. So just give me 2 minutes. I'll try to fix this issue and then come back to you. Right? You can also take 2 minutes break if you want. आदित्य, ये विशाल का है? सॉरी नहीं, नीचे है. ये मेरा ये नहीं हो रहा है. एक बार बुला कर देखो तो. उसको बुला बुला बुला. नहीं चल रहा. देखो पेन पे क्लिक किया. देखो उसको क्लोज करके कुछ करना है क्या? इसकी तरह चल रहा था. चल रहा है. ठीक है वो कर लूँगी मैं. चल ही नहीं रहा था, वो प्रॉब्लम था बस. ठीक है. थैंक यू. So, okay, students, I think we are quite back in the track right now. So the pen was not working. I tried to fix the issue, and we can solve this sixth question again, just in case if anyone have not got. That's it. So, okay. If you guys are not at any time at any point of the session, if you guys are not able to see the screen, just let me know. Fine. So this was the question. The value of 1 dB in coulomb meter is, so it's around, as you can see, mu is equal to Q into L, where the value of Q is 1.602 into 10 power minus 19, and value of L would be 0.02 nanometer. So you need to convert this to meter, which would be around 2 into 10 to the power minus 11, and this would be around 1.602 into 10 power minus 19, right? So then you can see how much it will come, around 3.3 something into 10 power minus 30 coulomb meter. So this was coulomb, and this is the charge and length. Fine. Okay, I think you guys were able to see my screen. Yes, it's working fine. So let's move on to the next question, which is the seventh question. Seventh question here is, the value of gas constant R is, the gas constant for an ideal gas is represented by R, and we have to know which is the correct value for this gas constant. So the options given here are 0.0821 atm liter per mole Kelvin. Option 2 is 8.314 atm liter per mole Kelvin. Option C is 0.0821 joule per Kelvin mole. And lastly, 0.0821 kilojoule per Kelvin mole. So any guesses for this one? So this is the basic value of gas constant R. Any of you have like chemical background, right? Okay, one answer I got, which is the B1. Samuel is saying that B is the correct answer, which is 8.314 atm liter per mole Kelvin. Okay. So no other questions, no other queries, or no other guesses yet. Okay, we'll look into what's the correct answer for this one. So the correct answer for this question is unfortunately not B, but it's A, which is 0.0821 atm liter per mole Kelvin. So you guys need to understand the units very clearly. If you are like jumbling up with the units, it will cause you in trouble when you are ultimately trying to solve the questions. So this is the basic value of gas constant R, which can be also referred to as 8.314 joule per Kelvin mole, and again it can be converted, the joule can be converted into calories, which will then come as 1.985 calorie per Kelvin mole. correct? So don't mix up this 0.0821 and 8.314 with their units specifically. Sometimes what happen is like you remember 8.314 but then you will link it with atm liter per mole Kelvin, or just now as it happened, you had this number in mind but you were not correct with the unit. So here it was 8.314 atm liter per mole Kelvin in the option B, and the correct answer is like 8.314 joule per Kelvin mole. Fine, I guess. This is quite clear, and this you need to just memorize it. Probably if the I don't think the value for this one will be given in your questions when you are going to appear for the test. So I think few of these units and as well as their values you need to remember. Okay, fine. Let's move on to the next question. So the next question we have is question number 8, which is taking, it is a numerical question I see now. Okay, taking the enthalpy of vaporization of liquid xenon to be 25 kilojoule per Kelvin mole per mole. Calculate the boiling point. So anyone, anything you can remember or anything you can recall? Related to enthalpy of vaporization of liquid or boiling point, anything. I think this was taught in lecture 2, probably. Yes, it was lecture 2. So the options here given are 257.15 Kelvin, 357.15 Kelvin, 300.15 Kelvin, and lastly 200.15 Kelvin. So, uh, so this B answer is for the last one, right? I think the question is quite clear or not. Okay, we'll just try to calculate and look into what's the correct answer for this one. So the correct answer for this one is option B, which is 357.15. We'll just see how we got 357.15 Kelvin as the boiling point for xenon with enthalpy of vaporization as 25 kilojoule per Kelvin per mole. So what does the Troughton's rule state? I think in lecture 2 it has been taught about the Troughton's rule, which is L vaporization is equal to H vaporization is equal to U vaporization plus PV, which gives U vaporization plus RTB. This can also be written as L vaporization by TB, and it actually is around 8 R, which values at 70 joule per mole per Kelvin. So from here you can see the question is taking the enthalpy of vaporization of liquid. So what is the enthalpy of vaporization of liquid here is this H is our H vaporization is our enthalpy of vaporization of this liquid xenon. So you can write it as H vaporization by TB. From the first equation you can see or yes, from this equation L vaporization by TB is equal to 8R. We can write it as H vaporization by Tb is equal to 8R, which accounts for 70 joule per mole per Kelvin. So we need to solve this, okay? So let's try to solve this one. So you got this as, so H of vaporization by Tb, okay, is equal to 8R is equal to 70 joule per mole Kelvin. Think it's visible to you guys?
Yes, ma'am.
Fine. So what does the question states? The question already has the value for the enthalpy of vaporization, that is 25 kilojoule per Kelvin per mole. So we have our H. So we have our H of vaporization as 25 kilojoule. Was it? Yeah, 25 kilojoule. Sorry, per Kelvin per mole. Okay. So you see that here it is 70 joule per mole Kelvin. So you can just change this in terms of joule. So if you change this in terms of joule, it will come as 25 into 10 power 3 joule per mole Kelvin. Fine. And now you can just simply put the value of H vaporization and as well as this to calculate the TB. We needed to calculate the TB, right? So our TB would be very easily, it would come as TB is equal to, can anyone tell what will be the TB? So TB will become H of vaporization by 70 joule per mole Kelvin, and this H of vaporization here we have 25 into 10 power 3 joule per mole Kelvin, right? So you just need to divide it and tell me the answer for this one at least. So you guys have calculator with you. So 25 by 70 and 10 power 3. So the answer would probably, if you calculate, if anyone can just take out your mobile phones or even calculator, anything you have in your hand, you can just easily calculate this one. So the answer will come at around, as we stated earlier, the answer was 357.15 Kelvin. Can anyone verify this one? Or I'll have to verify. Is it coming as 357? This came as,
Yes, ma'am.
357.15 Kelvin. Fine. I guess this is a simple like maths, you can calculate it. Okay. Any issue till now, or anything you cannot able to understand, because these questions are, I think, quite direct questions, and even for your assignments, I think in the week one assignments, as I just saw it, those questions were quite like straightforward. So any queries till now? Okay, let's move on then. So we have two more questions left. Both of them are numerical. So the next question is, taking the enthalpy of vaporization of liquid xenon to be 25 kilojoule per mole per Kelvin per mole, and assuming that the enthalpy is approximately equaling the energy of vaporization, that is U. You have to estimate the self energy. So this is a continuation for question number 8, but in question number 8 you were asked to calculate the boiling temperature, but here you are being asked to calculate the self energy. Anything relating to self energy you have in mind? Okay, I think this has also been taught in the lectures. It's also based on a simple equation. It's nothing like rocket science. However, we have been given four options. Option A is minus 4.15 into 10 power minus 20. Option B is minus 4.15 into 10 power minus 10. Option C is minus 41.5 into 10 power minus 20. And lastly, it is minus 41.5 into 10 power minus 15. So is the I think it is clearly visible or not? I hope it's clearly visible, or I'll increase the font. I think now it might be better for you guys. Yeah. So any try on calculating or doing this numerical? Anyone? Anything related to self energy? Okay, fine. We'll discuss what is self energy now. So fine. So first, let us see what is this based on. So the this self energy of vaporization for 1 mole of molecule is given as energy of vaporization, that is given as n naught multiplied by mu liquid. So what is this n naught and what is this mu liquid? So in the question only you have been asked about self energy. So this mu liquid is actually denoting the self energy, and n naught is the Avogadro number. Any one of you can tell me what is Avogadro number? What is the value of Avogadro number? So you can clearly see it's just you have to put in the value for Avogadro number and the enthalpy of vaporization, which is that is 25 kilojoule per Kelvin per mole. Fine, we'll try to solve this one as well. So in the previous equation, as you can see what it's written, energy of vaporization is equal to enthalpy of vaporization, which is equal to the n naught and the product of the n naught and self energy. So H of vaporization is equal to n naught multiplied by mu liquid. Fine. So we already have the value for this one. We know the value of this one. We have to calculate this, which is the self energy. And the question was basically about the self energy. So what you can do is you can simply calculate this. So in our case, this one was 25 kilojoule per mole per Kelvin, and we know Avogadro number can till now I think 6.022 into 10 to the power 10 to the power 23. Fine. So here also you just need to convert this kilojoule per mole Kelvin into joule. So it will be like this: 25 into 10 power 3 divided by 6.022 into 10 power 23, and you will get your self energy. So anyone just can calculate this. So this will go up, and you have to just divide 25 by 6.022. Tell me the value of 25 divided by 6.022. Okay, Samuel wrote the answer for Avogadro number. I missed it. So 25 divided by 6.022 is, how much is it? So the answer will probably come as 4.15, and then 4.15 multiplied by 10 power minus 20. Right. The 10 power 23, this will go up, so this will become 10 power minus 23 multiplied by 10 power 3, and this is 4.15. So ultimately we'll get 4.15 into 10 power minus 20. Fine. Now let's just move on with our next question. Yeah, fine. Samuel also gave the answer. It is 4.151. Fine. I think this is quite clear to you. The last two questions, 8 and 9, both of them were related to each other. I'm sorry, I think I lost my connection in between, but I think we made it right away. So any issues or anything you are not able to understand, we can just take it on from here, because we are just going to the last question. But we'll also try to discuss something, like as I said, you guys don't have your book, so I think we'll discuss some additional contents if you would like to discuss through the book. So I can show you the book, I can share my screen, and you can at least get a look into how the book is, and what kind of questions are available in the book. You can also practice those questions. It will be much better for you guys. So okay, let's move on to this last question, which is estimating the solubility of NaCl in methanol at 298 Kelvin. The options are also given here, like 0.002, next is 0.2, C is 0.12, and lastly it is 2. So how do you relate this solubility of NaCl? Can anyone think about what formula or what equation can be put on here? I think one of the questions which we discussed earlier was had this mentioned this term solubility. I think I am like, am I audible clearly to you, or because I lost my network in between, so I think it is working probably. So, any guesses, anything or relating to solubility? We just discussed it like 3, 4 questions earlier. Okay, fine. We'll try to solve this question. How we can estimate the solubility of sodium chloride in methanol at 298 Kelvin. So you can see that we have been given a certain value also, that is of epsilon at 32.6. Okay. So the correct answer for this question is, for this numerical, is option A, that is 0.002. We'll solve this question, how it came and how you can also try to solve. If you have pen and paper with you, please try to solve this question. I think this is a quite a bit not tricky, I would say, but I think if you haven't read the theory part, you will find it difficult. So solubility can be like, we can define the solubility using the Boltzmann distribution equation. I think this equation we learned earlier, or which we mentioned Boltzmann distribution equation earlier in one of the questions, that what can it be used to find for? Right. One was chemical potential, then number density, and third was solubility. So here you can see xs is equal to, xs is the solubility, right, is equal to e to the power minus delta mu by kt is equal to, if we open this one, we'll get exponential of e square by 4 pi epsilon naught epsilon a plus a minus kt. So this formula, I think this is a straightforward formula. You guys need to remember it. It's given in the book also. It's mentioned in the lectures also. This is a very straightforward equation. You just need to go through the lectures once. Try to write down whatever equations have been mentioned in the lectures. Then maybe you will try to relate everything. You will be able to relate everything. So fine. Let's move on in solving this question. How can we solve this one? I have space here. So select the pen. Okay. So referring to the previous equation, just give me a minute. This pen is not working. Just 1 minute. Okay, I think we are fine now. Okay. So it was given as xs is equal to exponential of minus e square by 4 pi epsilon naught epsilon a plus a minus kt. So you have to find this xs, which can again be written as x2 by x1 using the Boltzmann equation, Boltzmann distribution equation. So let us just put up the values. So E is the charge of an electron, which we already discussed. It is 1.602 or 609 around into 10 power minus 19 to the power 2 divided by 4 pi. Now what is this epsilon naught? Epsilon naught is also one of the constants which has the value of around 8.854 multiplied by 10 power minus 12, and epsilon as given in the question, it was around 32.6. So this epsilon varies according to uh, uh, the liquid. So here it is methanol. For methanol, epsilon value is 32.6, and then this, so the distance between the NaCl molecule is around 0.276 into 10 power minus 9 meter multiplied by kT. Okay, till at least till now. So wait, yeah. So I think in the question it should have been also mentioned the distance between the sodium and the chloride molecule as well, atoms as well. But I think if you once go through the book, you will realize these are already given or already specified in certain tables. We'll discuss it, which tables or which like which pages you can refer to for these uh, like standard values. So till now I think it is clear that what is the value of E, what is the value of epsilon naught, what is the value of epsilon, and what is this A plus and A minus, and again kT is there. So K is the Boltzmann constant and T is the temperature. So the temperature in the question, it was mentioned around 298 Kelvin. Fine. So yes. So the temperature in the question is mentioned around 298 Kelvin. And if you multiply this with the Boltzmann constant kT, the value of kT will come together as, let me write it down here. The value of kT will come as 4.12 10 power minus 21. So let's solve this question now. I think all the values you already know. Probably you can tell me what will be the final outcome for x2 by x1. If you can calculate, I'll give you a few minutes. I think you already know what is the value of pi, that I don't have to like tell, or maybe I can. It's 3.14. So 1.609 multiplied by 10 power minus 19 the whole square divided by 4 pi, that is 4 into 3.14 multiplied by 8.854 into 10 power minus 12 multiplied by 32.6 again by 0.276 into 10 power minus 9 and multiplied by 4.12 into 10 power minus 12. So just tell me what will be the final value. If you can calculate. If anyone has some problem with the basics of this math also, you can just raise your hand or tell me if you are not able to understand. In the writing is not quite clear, but when I was speaking it, I think you heard it and just went through it. I don't mind my writing skills, but I'm trying my best here. I'll write it down once again so that you can just calculate it at least. So x2 by x1 is equal to exponent. So when you square 1.609 into 10 power minus 19, so the final value will come as 2.566 multiplied by 10 power minus 38. So this is minus here. Then it will come as 4 pi, that is 3.14 multiplied by 8.854, 10 power minus 12, 3, 2.6, 0.276 multiplied by 10 power minus 9, and lastly it is 4.1 or 4.12 into 10 power minus 21. Can you give me the final value? What will be the power to E? Let me write it. E will come as around anything. So are you guys calculating with me? Okay, I'll carry on then. So this will come at around minus 2.566 multiplied by 10 power minus 38 divided by 4.1 will come as 10 power minus 9, 10 power minus 33. It will come something around this. Just cross check it if it's coming the same or not. So the final answer should come as this, that is e to the power minus 6.2. Can you confirm? Anyone can confirm that you guys are also getting the same result or the same calculation? Okay, fine. Samuel has said that he is getting the same answers. I hope everyone else, Smriti and Sonali, both of you are also getting the same results.
Yes, ma'am.
Okay, okay. So when you, so this is basic. Using calculator, you can just calculate the value for e to the power minus 6.2, which should come as x2 by x1 is equal to 0.002. So when you go back to the question asks that estimate the solubility of NaCl in methanol. Right. So here you can just write it as, since we started it from xs, you can x2 by x1 is xs, which will come as 0.002. The final answer should be 0.002, which was our option number A. I hope this question is quite clear and understandable to you. This basically you need to remember all the equations, then only you will be able to correlate the questions, and then of course you have to simply put up the values and calculate it. But even after putting up the values, and if you are not able to calculate it probably properly, you may get some different answers, which may again like lead to some wrong answers given by you in the actual assignment. So fine, I think we'll revise it once again. This was dependent on the Boltzmann distribution equation, and we tried to solve it as much as we could. So fine, this was the 10 questions we discussed today. Apart from it, I think I'll share you one. Do you know about the discussion forum as well? Whatever you will be giving in the discussion forum, I can just access it and I can also answer you guys there. So this is the discussion forum. Are you guys able to just look into my screen?
Yes, ma'am.
No, not the PowerPoint presentation. I'm sharing this uh, website. So
No, ma'am.
no, you guys are not able to see. Right, right. Yes. So that's what I needed to know from you. So let me just share another screen with you. Okay. So this is I think even for you also, you might have been included in this group, which is known as this discussion forum for biointerface engineering. It was, I think you guys have also been joined in this one, January 27, 2023. So here they have also mentioned to introduce yourself uh, and this is the discussion forum for biointerface engineering. So wait a second. Apart from this, I think whatever you guys will be uploading the questions, it can be uploaded from I shall share my screen only. Okay, fine. I think you are not now able to see my screen, but when you try to share your screen, it creates some problem. That's why I don't usually share my screen. So in the biointerface, in the Swayam portal only, you can just go to your course and there you can just ask a question using the tab. It's been just near to the about the course section, right? Okay, fine. So you can just post any of your queries there also, so I can look into it, or the any of the course or the team members can also look into it. So lastly, I think all the 10 questions were quite clear to you and it were easier. So okay, we can just discuss about the book, right? For the book, as I'll share the actually I'm not able to share extra PDF files from you. I'll have to again share the screen. Okay, let's see. So can you see the book here? So this is the book, Intermolecular and Surface Forces by Jacob and Israel H. Willi. Yes, I think it's visible, but this is the book you need to, like, you can upload like download it from internet. I think it is available in internet as well. If not, I'll be sharing this in Drive. And for example, the 32.6 for methanol, the epsilon value for methanol, it came from this table number 3.2. You can note it down. It's given on page number 65 of chapter 3. So this table states about the static dielectric constants of epsilon of some common liquids and solids at 25 degrees Celsius. So for methanol, we had the question which was asked for methanol. So the epsilon value was around 32.6. Similarly, you can find other questions, other tables which may be quite useful for you. I think it is like it should be made mandatory. Like if you don't have the book, it will be very difficult for you to learn this subject. So I would like recommend you strongly to download the book and study from the book. So fine. Um, as of now, we are done for the session, but if you guys have anything to discuss with me extra, like any other queries apart from the questions you guys are facing for this for this course, so we can discuss that. I think there is no query. So next, for the next session, what I will try to discuss more of the lecture also, like whatever has been taught in the lecture, like for week 2. For week 1, I couldn't like update it. However, I mentioned the recap just with the like topics, but next time we'll be discussing it in detailed. Okay, so that yes, I can upload the book. I will upload the book, but not here because I don't have any facility here where I can upload the book. I will upload it in Drive probably, and the Neptel team will share you the Drive link where you can access the PDF of whatever the presentation which has been discussed here, as well as the books. If not, if you don't get the Drive link, just I think you don't have my mail, um, or if if not, in the next session I will probably till the next session, if you don't get the Drive link, then just remind me once so that I can give you my mail ID, and there we can just exchange the books. Fine. So this was all about our week 1 assignment, and we share my okay, one of the student joined very late. So what I will do is I will rather go through the questions once more, uh, very fastly. Yes. So I think you are able to see this window. So we talked about the first question was about van der Waals forces are also termed as. So all of the above was the answer. It can be also known as dispersion forces, Keesum interaction, as well as Debye forces. So we discussed why these forces can also be termed as dispersion, Keesum, and Debye forces. Next, we went through which one of the following is true for van der Waals forces. So we were given the 4 options, and one of the options among this was true, and other of them were false. So we discussed basically what are the characteristic or what are the specific features of van der Waals forces. So you get to know that these are um, the covalent and ionic bonds are significantly stronger than the van der Waals forces and not weaker. Van der Waals forces are also long range forces. They may be repulsive or attractive. And lastly, they are non-additive in nature. Okay. Next question was, my potential is also termed as NM potential, interaction pair potential, Lennard-Jones potential, or both A and B. So we knew that already that interaction pair potential is given by my potential, but apart from that it is also termed as NM potential and not Lennard-Jones potential. So we discussed the difference between LJ potential and my potential, what is the equation relating to it, and when was it proposed. So Lennard-Jones potential was proposed way after from my potential in 1924, and my potential was proposed in 1903. So next was relating to the hydrophobic or next was relating to the forces which stabilize the structure of DNA. All of the above was the answer, as DNA is being stabilized by all hydrogen bonds, hydrophobic interaction, as well as the van der Waals forces. Okay. Next was, which among the following does the Boltzmann distribution equation helps to find? So Boltzmann distribution equation helps to find us all of the above, that is the chemical potential, number density, as well as the solubility. So all these three, we did solve one question relating to the solubility, how Boltzmann distribution equation helps to find the solubility. So these were the equations involved for finding out the chemical potential, number density, solubility relating to the Boltzmann distribution equation. Next was, what was the value of 1 dBi in Coulomb meter? Coulomb, we talked about dipole moment, and thus dipole moment has its unit as dBi, and dBi in terms of Coulomb meter can be represented as 3.336 into 10 power minus 30 Coulomb meter. So how did we solve this? So dipole moment can be written as mu is equal to Q into L. So Q is the charge present and L is the distance between those two charges. So here we multiplied the charge of an electron by with the distance between these charges. So we got the answer as 3.336 into 10 power minus 30 kilometer. But you need to remember that all the units should be similar. So the question was asked in terms of Coulomb meter, and I wrote here the distance as 0.02 nanometer, which must be first converted into meter, and then you must go for the calculation. Fine. Next was, what is the value of gas constant R? So R is basically the gas constant of an ideal gas is represented by R. And the answer for this question was A, that is 0.0821 atm liter per mole Kelvin, which can be also written as 8.314 joule per Kelvin per mole, and it can be also converted in terms of calorie, which is 1.985 calorie per Kelvin per mole. So you need to remember every units, and you must see what the question is asking from you, and then you must just apply the units correctly. Don't just confuse between 8.314 and 0.0821. Eighth question, we talked about the enthalpy of vaporization, was given to us as 25 kilojoule okay. So 25 kilojoule per Kelvin per mole was the enthalpy of vaporization of liquid xenon was given to us, and we were asked to calculate the boiling point in terms of Kelvin. So here you are already in the question, it's already been mentioned Troughton's rule. So you just need to remember what is Troughton's rule and correlate the question with it. So we tried to also solve this. So in terms of Troughton's rule, enthalpy of vaporization by boiling point is equal to 8R, that is 70 joule per mole per Kelvin. If you are able to just recall this equation, you may just simply put the value of this enthalpy of vaporization, that is 25 kilojoule per Kelvin per mole, and your boiling point will easily be calculated. So I tried to solve this also, but the writing is not that clear. I hope it's quite easy to understand. Like you have to find out TB, and you have to convert 25 kilojoule per Kelvin per mole into 20 into in terms of joule. So it will come as 25 into 10 power 3 joule per mole Kelvin, or per Kelvin per mole, divided by 70, which will lastly come as 357.15 Kelvin, which was our option B. Fine. Ninth question was a continuation of question number 8, where you have to rather estimate the self energy and not the boiling point, boiling temperature. So in this case also you need to just recall the Troughton's rule and apply the enthalpy of vaporization of the value of enthalpy of vaporization of liquid xenon. So here also we try to uh, solve it using the energy. The self energy of vaporization for 1 mole of molecule is given as energy of vaporization can be written as equal to enthalpy of vaporization is equal to Avogadro number multiplied by self energy. So self energy can be calculated as an enthalpy of vaporization by Avogadro number. So here also you need to remember to convert the enthalpy in terms of joule and not kilojoule. Fine. And last question was estimating the solubility of sodium chloride in methanol at 298 Kelvin. So we probably did this question on the basis of Boltzmann distribution equation. So where solubility can be written as exponent of delta mu, that is the self energy, by kT. So this equation you may find in the books as well, as I said earlier, and I think this has been discussed in the lecture also. So simply putting up the values, uh, however, you need to remember two things, that is epsilon for methanol here it's 32.6, and the value of kT, the Boltzmann constant, and temperature is 298 Kelvin, as well as the distance between the two atoms of NaCl, which is approximately 0.276 into 10 power minus 9. So this value also you may get in the book, or if you get such questions, I think probably they will be giving you the question, they will be giving you the values. Other than that, I think you can just um, remember these standard values. For example, for water it is around 78.5. As such, in case of methanol it is 32.6. Right. So we discussed this question also in detail. And lastly, I would welcome you all in the next session as well. And thank you for being so patient and listening and attending this whole 2 hours lecture. It's a quite long discussion session. Uh, I'll try to incorporate few of the other things in in the other sessions, so it may sound or it may be a bit better than this session. So any feedback you want to give or anything you want me to add in the next session for you? I'll try to discuss everything which has been taught in week 2 for the next session. So I urge you guys, if you could just go through the lecture of week 2 before coming to this session, so that whatever equations I am at least putting up here, you can easily recall it and remember it and correlate it. First of all, mainly you need to correlate every equation, whatever the question is given, you need to actually correlate what kind of equation or to be used for solving the question. Okay, fine. So I think last time I couldn't share the book properly, but if possible, let me share you the book. I can show you the book. Yep, I got it. Okay, fine. So this is the book I am talking about. That is Intermolecular Forces by Jacob and Israelich Willi. This is the third edition which I have, and you may just note it down. If you could get it even before getting the drive link from me, then it would be better for you to learn and easier for you. I hope you are noting it down, since you said that it's not available in the Swayam portal. Yes. So as I said, 32.6, this is the table 2.1, which gives the boiling temperatures and the latent heat of vaporization of some common substances. This is table 3.2 in page number 65, from where we took the dielectric constant, that is epsilon, in our question. While solving the question, we required the dielectric constant of methanol, which can be taken from table 3.2. Similarly, you can see it has the dielectric constant for water, D2O, that is 77.9, and water in terms of H2O, it is 78.5. Try to remember these some of these values so that you just don't need to go back to the table every time. Water, for water you can remember it's 78.5. Let me highlight it. Okay. Also, few of the questions here are written, I think. um, so yes, look here. The second question, third question was, my potential is also known as NM potential, interaction pair potential, Lennard-Jones potential. So here you can see my is also regarded as NM potential. So I already discussed the equation for it, minus A by R power N plus B by R power M. And Lennard-Jones is a quite different thing than my potential. It is A by minus A by R power 6 plus B by R power 12. So it is a revised version of my given by Lennard-Jones. Apart from this, I would also like you, if in the book it's so we talked about the distance between the charge atoms of NaCl, right? So how much was it? It was around, I guess it was around 0.276. So let me find it and show you that as well. Yes. So see, few of the radii of molecules have been given here, such as CH3OH, CHCl3, C6H6, CCl4. So mean radius and van der Waals forces are given here. That is what I meant, that various tables you need to refer in the book so that you can understand from where the values are coming and how can you just solve the question, because it's not easy to learn this subject without the book. Of course, book should be there. So fine, I think we may sum it up for this session. So any feedback you would like to give or add, like I should add more questions. Like for this session, I tried to discuss 10 questions. If for the next session you would like to discuss more, then you can just write it in the discussion forum also, or you can just post it here in the next session. Fine. We'll leave for we may just sum it up, and we'll meet in the next session, that is on Tuesday from 7 to 9. Okay. You guys can leave now. Good night, and just try to learn whatever has been taught, because this course runs very fast and it has a lot of things that you need to understand before moving ahead. So fine. Good night, everyone, and we'll meet in the next session. Thank you.